We will now look at the liquid state. Liquids, as you know, are a metastable state. If one looks around, they are not common in the universe. You can't swim to the moon, there are no oceans on Mars. They actually only exist in a narrow range of pressure and temperature. This is because liquids exist in equilibrium with gas. If one has a liquid, it is constantly evaporating with a known vapor pressure, P sub V. It is only condensed by the force of an external pressure, in the case of the Earth, the atmosphere. We'll call it PEX. Vapor pressure, as you learned in general chemistry, exhibits an Arrhenius type of behavior. The log of P2 over P1 is equal to delta H of vaporization over R, 1 over T1 minus 1 over T2. Therefore, vapor pressure is a function of temperature. The boiling point is the point where the vapor pressure exceeds the external pressure, or PV is equal to or greater than P external. The normal boiling point, which is recorded for most liquids, is the temperature at which the vapor pressure is equal to 1 bar. We'll start by looking at what is called the internal pressure. The internal pressure is essentially the sum of all the repulsive forces between matter in a condensed state. For a real gas, as opposed to an ideal gas, the van der Waals equation generally applies, which states P plus A over V bar squared times V bar minus B is equal to RT, where V bar is the molar volume expressed in meters cubed per mole. A is the sum of all the intermolecular attractions and repulsions, which would either increase or decrease the apparent pressure. B is called the internal volume. Remembering, for an ideal gas, the volume of the gas itself is assumed to be 0, but in reality, gas molecules do have a volume. The internal pressure, thermodynamically, is the partial change in the internal energy versus volume at a constant temperature. This solves to T times the change in P versus the change in T at a constant volume minus P. Remembering from thermodynamics, delta U is Cp dt minus PdV, where the heat capacity at constant pressure is actually the change in internal energy versus temperature at a constant volume. This can be converted to the partial in pressure with respect to temperature at a constant volume dt minus PdV. So, when taken as a partial with respect to volume, the internal pressure solves as the van der Waals constant A over the molar volume squared. The implications of this can be seen in water at 25 degrees C, 1 bar pressure. For water, the van der Waals A constant is 0.5536 pascals meters to the 6th per mole. And as you know, under ordinary conditions, water exists as a solid, liquid, or a gas. If one looks at the gas state of water, the molar volume is 0.0245 meters cubed, based on the ideal gas law of 1 mole of any gas at 25 degrees C, 1 bar, having a volume of 24.5 liters. Therefore, the internal pressure is 0.5536 pascals meters 6 per mole, divided by that internal volume, 0.0245 meters cubed squared. That gives you an internal pressure of 924 pascals. In this case, the gas state, that internal pressure is much less than the external pressure of 1 bar, or 10 to the 5th pascals. However, when one looks at the liquid state, water has a density of 1 gram per centimeter cubed, which means the volume of 1 mole would be 18 milliliters, or 1.8 times 10 to the minus 5th meters cubed. Therefore, the internal pressure would be 0.5536 Pascal meters to the 6th per mole divided by 1.8 times 10 to the minus 5th meters cubed squared. That would give an internal energy of 1.7 billion pascals. This is 10,000 times higher than the external pressure. Liquids keep their form due to something called surface tension, gamma. This forms the boundary between the liquid and the vapor phase. It arises because surface molecules are only 50% coordinated. Half of them lie below the surface and half of them are exposed. Therefore, extra work is needed to hold the surface together. Surface tension is a type of two-dimensional isothermal non-PV work. As you recall, under a constant temperature, delta G is the integral of VdP in joules, where delta G is the definition of non-PV work, in other words, non-mechanical work. Work is defined as force times the distance and is therefore three-dimensional. Force is the two-dimensional equivalent of work, where the force to keep a surface together is equal to the surface tension gamma times 2 times the radius of the particle. For a droplet to be stable, gamma must be stronger than the difference between the internal pressure, P sub I, and the external pressure, P external, or must be greater than delta P. Therefore, on the perimeter of the bubble, delta P times pi r squared must be equal to pi times gamma times 2 times the radius for the bubble to survive. In other words, delta P must be 2 times gamma over r for a stable bubble. The Gibbs free energy, however, once again, is the integral of VdP, or the molar volume times delta P. That molar volume times delta P is equal to the molar volume times 2 times gamma over r by bringing the previous equations together. As you saw in the previous slide, delta P is always positive and large in this case. Therefore, as the radius of the bubble decreases, delta G becomes even more positive, and liquids should not exist at all. As mentioned, the internal pressure of a liquid is always several orders of magnitude larger than the external pressure. Also, the surface tension, which holds a liquid together, is inversely proportional to the radius. Therefore, small droplets should not exist. Therefore, it should never rain. How come we have liquids on Earth? This is due to a process called adsorption. As mentioned, surfaces are only half coordinated, with half the molecules lying in one phase and half in the other phase. Therefore, surfaces are reactive. Molecules on the surface wish to cover themselves by a process called adsorption, which is in equilibrium with desorption. Both are first-order kinetics. The rate of absorption is equal to a rate constant, call it Ka, times the concentration of A times 1 minus theta. The rate of desorption is equal to another rate constant, Kd, times theta, where theta is simply the fraction of the surface covered, and A is the adsorbing species. Since these two processes are in equilibrium, and R adsorption is equal to R desorption, the ratio of theta over 1 minus theta is equal to the ratio of the rate constant of adsorption, Ka, over the rate constant of desorption, Kd, times the concentration of A. And the ratio of these two first-order rate constants becomes an equilibrium constant, capital K, times the concentration of A. If you recall, the standard Gibbs free energy is equal to minus RT log of the rate constant K. Therefore, as the fraction of the surface covered theta approaches 1, theta over 1 minus theta approaches infinity, and delta G becomes more negative. Addressing the question that wasn't said or answered at the beginning of the slide, why is a car dirtier after it rains, comes down to the fact that nothing is stronger than dirt. The only reason we have liquid water on Earth is because there are particulates in the air. Water droplets require microparticulates to form. That gives them the energy to overcome the external pressure. If there was no dirt in the atmosphere, there would be no rain, and if there was no rain, there would be no oceans. As you learned in freshman chemistry, the definition between the solid, the liquid, and the gas phase comes down to intermolecular forces. However, you were given an incomplete arrangement of those forces. The strongest forces are ion-ion forces, the forces that make salts solids. In this case, you are basically talking about Coulomb interactions, where the force is the charge on A times the charge on ion B times the fundamental charge squared over 4 pi epsilon 0 r squared, where the attractive energy is the charge on A over the charge on B times the fundamental charge squared, 4 pi epsilon 0 times r. As you know, energy is force to a distance. You will notice in the next few slides of the next few items, the difference between force and energy is actually a factor of 1 over r. There are many variations of energy and force. In freshman chemistry, you learned about dispersion forces, hydrogen bonding, and dipole-dipole interactions. There are variations on those. Next, you saw there could be an ion attracting an ion. Ions will also attract a dipole, where the difference between the forces involved is simply the dipole moment mu times the cosine of the angle of approach theta, except this falls off as r cubed, which means the energy falls off as r squared. There are also dipole-dipole interactions, which are the easiest to understand, which depend upon the dipole moments of A and B, and are inversely proportional to r to the fourth, which means the attractive energy is r to the third. Intermediate between dipole-dipole forces and dispersion forces, you can have dipole-induced dipole forces, where the force is again related to the dipole moments of A, but the polarizability of B, alpha, times the fundamental frequency of the change of that polarizability. This falls off by a higher factor of r to the fifth, and therefore the attractive energy is inversely proportional to r to the fourth. The weakest intermolecular forces are dispersion forces, also called van der Waals forces, essentially induced dipole to induced dipole forces, called London forces in other sources. These fall off dramatically, being inversely proportional to r to the 7th, and are proportional to the polarizability of A and B, and the attractive energy falls off as r to the 6th. Beyond this, you have repulsive forces. Since two particles cannot occupy the same space at the same time, repulsive forces increase rapidly with distance, where beta is a critical distance and is inversely proportional to r to the 13th, and therefore the attractive, or in this case repulsive energy, falls off with r to the 12th. In all of these relationships, epsilon sub 0 is the permittivity of a vacuum, or 8.8 times 10 to the minus 12th coulombs per meter squared. Epsilon is the dielectric constant of any given particle. As mentioned, theta is the angle of approach between two different dipoles. Mu is the dipole moment. Alpha is the polarizability of a bond. Beta is the critical distance between two particles, essentially interest to R1 plus R2. And R is the actual separation of the particles. From these various relationships, solubility can be determined. It's a simple question of adding up all of the solvent to solute interactions and asking oneself, are they greater than the solute to solute interactions? The interesting thing about liquids is, as mentioned earlier, they are a metastable state and uncommon in the universe, and therefore can be equally well described by two different theories. The first theory is the lattice theory, which holds that liquids are loosely bound solids. If one looks at a solid crystal, such as sodium chloride, there is both long-range and local ordering. Centering on the sodium ion, each sodium ion has 8 nearest neighbors, 6 next nearest neighbors, 12 next nearest neighbors, and so on to infinity. There is only vibration and no movement, therefore there is no internal reordering in a solid. If one looks at a liquid, however, such as H2O, the local ordering is strong. There are 6 nearest neighbors. The next nearest neighbors always have a coordination number of 18. However, the occupancy constantly changes as water molecules move in or out. Additionally, there is no fixed coordination in further shells of occupancy. The theory that a liquid is a loosely bound solid is shown in the extreme. Many of your cell phones have liquid crystal displays. In this case, the display is held at a state that is close to but not equal to the freezing point, so the liquid can still move but move slowly. More commonly, common window glass is essentially a frozen liquid. In European medieval cathedrals, the great stained glass windows have to be repaired constantly because as the glass hangs vertically for centuries, it begins to flow like water and eventually will fall out of the window unless the windows are maintained and rebuilt. Alternately, a liquid can be thought of as an extremely dense gas. This is called the free volume theory. The volume a molecule can move before colliding with another molecule at a distance a can be simply described as the volume of a sphere, 4/3 pi times a cubed. However, the molecules themselves occupy space, and the molecules have a diameter d, and within this diameter, no two particles can exist. Therefore, one has a free volume, where V sub f is equal to 4/3 pi times a minus d cubed. This seems trivial, except if one looks at it by comparing liquids to solids with the speed of sound. As you are aware, speed, velocity, is proportional to a distance, in this case, a. For an ideal gas, the d value, the molecular diameter, is said to be 0. Therefore, for any medium, the speed of sound ideally divided by the actual speed of sound is going to be a, the distance traveled, divided by the distance traveled minus the molecular diameter, or the free volume. Interestingly, for any known substance, this relationship is continuous. There is absolutely no discontinuity at the liquid-vapor phase transition in this ratio. Therefore, liquids are extremely interesting because either theory equally well describes their behavior.